At first glance, sugar and salt may appear similar. But beware, confusing them can ruin your morning cup of coffee. I think I'll just put this away. So let's use chemistry to explore these differences. At the macroscopic scale, sugar and salt both appear as small white crystals. But let's zoom in and examine them at the atomic scale. You'll see in both substances, the particles are arranged in a lattice. However, the sugar lattice and the salt lattice are different from one another. The difference between the two involves the type of particle within the lattice. With sugar, we just have one type of particle, and each particle is a sucrose molecule, C12H22O11. However, salt is a different story. Its lattice is made up of two distinct ions, sodium and chlorine. These aren't bonded together in the same way that carbon, hydrogen, and oxygen are in sugar molecules. In fact, the sodium and chlorine atoms in salt exist as ions. Ions are atoms or molecules that possess an electric charge when they have either gained or lost an electron. The sodium ion has lost an electron and therefore has a positive charge, while the chloride ion has gained an electron and thus has a negative charge. Ions with a positive charge are called cations, whereas those with a negative charge are called anions. One trick to remember that cations are positive is that cations have a T, which looks like a positive sign. Let's take a look at the atomic scale for both salt and sugar and see what's different about how they behave when they dissolve in water. The sugar molecules float off or disperse into the water, but the ions of salt dissociate from one another. Their bonds are broken when the salt dissolves. This is in contrast to the molecular bonds in sucrose, which remain intact when it dissolves in water. We can demonstrate an interesting effect of this behavior using a light bulb. Here, I have 3 glasses of water. One, 2, and 3. We will keep this first glass of water as a control. In the second glass, I'll add some sugar. And with this third glass of water, I'll add some salt. When I run a current through them with this specialized conductivity tester, first in just water, then in the sugar solution, and then in the salt solution, we see that only one of them conducts electricity and the bulb lights up. Why is that? Well, the saltwater solution is an electrolyte, which means that it has positive and negatively charged particles floating around in it. Electricity requires charged particles to carry the electric current. In the salt solution, the sodium and chlorine ions are charged particles that can move around. They carry current and complete the circuit that lights the bulb. So how do we expand our chemistry language, the symbols and models of chemistry, to handle these distinctions? One way is by using the name molecular compound for substances like sugar and ionic compound for salts. This language conveys that the particles in a molecular compound are molecules, while the particles in an ionic compound are ions. We also have to extend our use of chemical formulas. For a molecular compound, we give the chemical formula of the molecules, which for sucrose is C12H22O11. This formula communicates that the particles in sucrose are molecules, each with 12 carbon, 22 hydrogen, and 11 oxygen atoms chemically bonded to make a single molecule. For an ionic compound, we have to convey the composition of each type of ion that is present, which in this case is a positively charged sodium and a negatively charged chloride. Since these ions are present in equal amounts, we can focus in on one pair of them, which we call a formula unit. The charges in a formula unit will sum to 0. So we also drop the charges, writing NaCl instead of Na plus and Cl minus. Okay, so why are there equal amounts of sodium and chlorine? Well, for any substance, the overall charge must be neutral. In other words, the substance as a whole must have no net charge. We can't have a macroscopic sample of just sodium plus or chlorine minus. But we can have as much salt as we want, so long as there are equal numbers of sodium plus and chlorine minus. If they are present in equal amounts, the sum of the charges is 0 and we have no net charge. In everyday use, the word salt usually refers to table salt, the sodium chloride compound we've been talking about. However, in chemistry, the term salt encompasses a broader range of compounds with different properties and compositions. We see these other salts in everyday use as well, like copper sulfate, used to get rid of algae growth in ponds, lye or sodium hydroxide, which makes soap and cleans drains, or even lead nitrate, which is used to make matches. Unlike sodium chloride, some of these salt compounds contain ions with more than one atom. But some of these salts, like lead nitrate, can actually be fatal if ingested. In fact, all lead salts are toxic. This is why I would strongly recommend never eating or drinking in a chemistry lab. You'd have to be very careful in selecting which salt you add to your snack or coffee. Stick with table salt, good old sodium chloride. Okay, so we previously introduced the concept of ionic compounds. These are ions which are held together by their positive or negative charges, like the positive sodium ion and the negative chlorine ion, which make up table salt. However, not all salts or ionic compounds are composed of just 2 ions. Consider, for example, lead nitrate, which makes up matches. What do you think will happen when lead nitrate dissolves in water? The lead nitrate is made up of 3 ions, the lead cation and 2 nitrate anions. Therefore, it'll dissociate into 1 lead ion and 2 nitrate ions. The anion, nitrate, has 1 nitrogen and 3 oxygens bounded together into a single particle. Each particle has a charge of 1 minus, or NO3 1 minus. The cation, lead, has a charge of 2 plus, or lead 2 plus. For the compound to be neutral, which is to have a net 0 charge, there must be 2 nitrate anions for every lead cation. Therefore, our formula unit for lead nitrate is lead NO3 2. And there you go. Now you know a little bit more about a chemical compound that we interact with in the real world every day.